We now start chapter 8, which is conservation of energy. And this is basically the whole chapter is based on energy conservation. So if you look at the what we call the law of conservation of energy, and that law says that energy can neither be created nor destroyed. So if we have a system and we have a number of objects inside it, the energy content of this system would not change, will remain the same unless some energy enters it, in which case it would increase, or if some energy leaves it, in which case it might decrease. So the net change in the energy, not the internal energy, but the energy content of this system would depend on how much energy is coming in and how much is going out. So in what we call an isolated system, in which nothing is coming in or going out, then the energy change would remain zero because no energy is coming in or going out. So we would essentially be looking at this. We'll look at energies coming in, energies going out, and finding the change inside, which is simply the outflow minus the inflow. The inflow is more than outflow, then the energy content increases. Now as we write this, we need to remember that the energy can either be kinetic or potential. So these are the two kinds of energies. There are cases where when we have friction and something gets heated up. So for example, you're pushing this and there's friction backwards, and as this moves along to the right, it rubs against the floor, and normally the temperature would rise. So the work done by friction goes into the internal energy of this object. And by internal energy, we essentially mean a change in temperature. A change in internal energy would be a change in temperature. Internal energy is related to the temperature. So even though temperature is essentially the average kinetic energy of all the molecules inside this material, and so a rise in temperature is really a rise in kinetic energy of the individual molecules, and therefore internal energy is not a separate energy in itself, but it's just kinetic energy. So we could simply say kinetic and potential, but in this textbook and in places we add a term internal energy, which considers a change in temperature. So we would have a situation in which we have some kinetic energy, we would have some potential energy, which we write as U, and we would have some internal energy inside here. And there are energies coming in and going out. So let's see what is the way in which energy can come in or go out. And these are what we would call energy transfer mechanisms, let's say. How can energy come in or go out? Well, there are many ways. The first is work, which we write as W. So if you do work on this system, you can change the energy of that system. So that's the work. We could add some heat to the system, and that would go primarily into the internal energy, but could also change other things. So this is one way of doing or transferring energy to the system. That's a second way. And we have a few other ways also, such as the transfer due to mechanical waves. Now, sound is a mechanical wave, and sound can transmit energy into an object. Earthquake waves are also a form of mechanical energy, so that they transfer a huge amount of energy. And then we have other kinds of vibrations. So these are all mechanical waves which transfer energy from one place to another. Then we have matter transfer. So transfer energy through matter transfer. So if you have your system here and a mass enters this system, it will bring with it some internal energy, some kinetic energy, and maybe potential energy. Whatever it brings with it, that adds into the system. Or if some mass leaves it, well, then that's a decrease in its energy. So matter transfer brings with it or takes away with it some energy. Then we have electrical transmission. So if you have like electrical transmission, so for example, if this room is considered a system and we have electric wires coming in, and well, the wires go out, and if we turn on a heater here or we turn on a lamp here and that gives off light or gives off heat, we can change the internal energy of this system, or we can operate a motor or some other mechanical device and do some work inside. So electricity comes in, well, some electricity goes out. So that is a form of transmission of energy through electrical energy. And then we have electromagnetic radiation. Okay, so electromagnetic radiation is like sunlight or heat rays. Well, heat rays is not a proper word, but we can have energy coming through visible light or infrared or other forms. So if you have, for example, your room here and you have a window here and the sun is bright and sunlight comes in, all that could heat up your room. So that's transfer of energy through electromagnetic radiation. Now in this chapter we won't be concerned very much about these kinds of transfers of energy. We'll also not be concerned with the heat. We'll just be concerned with work and the changes in kinetic potential and internal energies. So basically we're looking at mechanical energies rather than other forms. Now to write the equation for the energy inflows and outflows and the change here, we would write an equation like this, that the energy transferred, which could be due to all of these, but we'll stay with the work part, is equal to a delta energy of the system. Now the energy transferred could be due to the external work, which is our W, and the energy of the system increased or decreased could be a change in the kinetic energy, a change in its potential energy. Okay, we have the two kinds here, kinetic and potential energies, or it could be a change in the internal energy, not U, that's reserved for potential, E internal, and that would become our general equation. Normally we write it in a slightly different way, so we'll write it as delta K plus delta U plus delta E internal equals sum of the external works. There may be more than one external force is acting, so we add them all up. Now, before we go further, let's see internal energy a little bit more. And we saw here that it was because of the friction would create some heat, and that would cause a change in temperature, which is a change in internal energy. And therefore, the internal energy that we are dealing with is not because of any heat flow, because we are not considering heat in this chapter, but it is because of friction work, which is Fd. So if you look at delta E internal a little bit more, this is due to the friction work, the work that would cause heating on the surface, and the friction work would be the force times the displacement, which would be Fd. And so we can replace this with Fd. And instead of worrying about whether they're in opposite directions, because it will always cause an increase in the internal energy. Friction would always cause heating. Friction cannot cause a decrease in temperature. So it would be added to here, and we put these absolute signs so that we don't worry about the direction of F and D, whether it's positive or negative, or they're in opposite directions. So we just take Fd absolute and we add it to it, or as written also sometimes, we take it on the other side and write it over here, indicating that it's a form of external work, which is negative. So that becomes our equation. We could use it this way or use it in this way.